to be building some Pytorch, more tutorials. Today we're going to be doing convolutional neural networks, CNNs, which is, you know, not like the news network. This is a convolutional neural network. It's for AI, specifically when you're looking over two-dimensional data. What's two-dimensional? Well, videos and images, of course, where you want to add relationship meaning in between neighboring pixels. All right, because you're gonna have a grid, and this pixel right here is gonna have meaning next to other pixels. Hey, Torva, good to see ya. Happy Monday. Glad you're here. Hey, thanks for saying hi there. It was Bra Machina. Thank you. Good to see you again as well. We are going to be doing convolutional neural networks today. Really excited about this. We've got our tutorial up and running. It looks like a very simple getting started. We're going to go through the whole thing. This is part 2 of the Pytorch tutorials. Last week, we went through an entire segment of all basics. It was a little bit more than a basic. I think we did pretty good, though. Let's just start typing some code. All right, so then, let's see, it'll call cnn.py. All right, so this will be our CNN. Import torch. And then we're just going to follow along. These are the very basics. Hey, Developer Exotic, what's up? Good to see ya. We're off onto our CNN convolutional neural network. We're continuing becoming a Pytorch expert. We're going to do it. We made a lot of progress. It's going to happen. Let's go through. So as you see here on the screen, it's going to go through some basics, and then it's going to jump very, very quickly into some heavier stuff. Right here. Oh, boom, instant, boom, convolutions, right there, convolutions. Multiple feature maps, really the filters, right? The filters, you guys. And then more feature maps, and even more, and it keeps going from there. Hey, how's it going? I try hard. Hey, Steven, good to see ya. Welcome on in. We're going to continue our Pytorch adventure. We're going to become the best Pytorch experts ever. That's the plan. That's the plan, you guys. Hey, Steven, man, how are we doing? We're doing good. Claude, hey, good to see ya. Welcome on in. We are getting started with our Pytorch tutorials, you guys. All right, so let's go through this real quick. We'll say z equals torch dot rand. Is it dot random or dot rand? Was it rand? Yeah, no, torch dot zeros. Zeros. All right, spelled weird. If it isn't the person who's taking jobs from people, oh no, just a little bit, not like a lot. Just a few. Here is my second like. Oh, there we go. Hey, Claude, thank you very much. Appreciate it. All right, so we've got our zeros. Thank you for the hearts. Let's see. Wait. Oh, 5. Okay, sorry. So let's make it. Let's do a 5 by 5. So it's pretty and organized. All right. So you can think you just print z, right? Something like that. Print the z. What are we doing today? We are becoming Pytorch experts. Part 2. We're going to create a convolutional neural network. We're going to have relationships with two-dimensional items, images, right? Video. See how this number is 0.93 at the very beginning here. So we'll say it says 0.9390, right? If we run this again, it's going to be different, right? See, now it's the first element is 0.0123, and we run it again, it's going to be different again. 6485 right here, right? This is what I'm looking at, 6485. If we turn on manual seed, it's going to guarantee that it's always the same. So watch this. 8217, 8217, 8217. It's always the same. Right there. So you can see it. Right there. So you can kind of see. All identical. 0.8217, which is kind of great because if you want to have a deterministic, every single time, always getting the exact same kind of accuracy and having the exact same model every time you run it, then you can use manual seed. However, you might want not to do this because you might want to have some randomization in there. Having different random weights across all of your matrices can give you a better outcome on your model. I've seen this happen many times. You can train it once, train it again, and train it again, and you will get different capabilities with every single new model. So you can see R1 and R2. There we go. Print that out. Before we hit the error case, you can see that they're two differently shaped matrices. One is a 2x3, the other is a 3x2. You can see this one up here is wide, right? is like sort of wide and short. The other is taller and skinny, right? So if we try to merge these together, like let's try adding them together. R2 print. It's going to give you a runtime error because they are not the correct shape. However, I do believe you can multiply these. I think you can multiply these. Here we go. Let's try that. All right, so that's a problem. You can't add them. Can you multiply them, though? AI intelligence. Hey, who was that? Raton Dulce. Let me hold on. Wait, Raton Dulce. Is that how you say that? Raton Dulce? Raton Dulce? Can you do multiplication? All right. I think you might be able to. I'm not going to ask you all. I'm going to ask you all. Do you guys know? Hello, Stephen Brock. Good to see you. Welcome on in. Can you do this R1 times R2? Error or not error? R2 equals will this work? Question mark. So will this work? Yes or no? Or will it crash? I'm actually curious about that. You can do R2 times R1. I think you can. You can if you transpose one of them. Hey, keep going. All right, so will this work? I think it might, or we might have to do this dot T. One of the two. Otherwise, or we might have to do that. Like we might have to do the @ sign. I think but let's just try multiplication first. Will it give us a runtime error? 3 by 2 times 2 by 3 possible. 2 by 3 times 3 by 2 is not possible. Really? Oh, yeah. Yep, you know it. I can see right there. Look at that. Because they match up. Well, do they though? Do they? Because the 3's match up with each other, right? On either side. All right, we're going to find out. You guys ready? Runtime error or no runtime error? Oh, there's a runtime error. Uh-oh. That doesn't work. You have to transpose them. You might be able to do it with the @ sign, so it's a matrix mult. Let's find if the matrix multiplication does work. Yeah. So the @ symbol will automatically transpose them. So you do .t, that will work, right? That'll work. Hey, that'll work. See, there it goes. You need the .t. Hey, because you're doing matrix multiplications instead of doing some convolutional neural networks. If you're familiar with the idea, it is just a slight variation on how feed-forward neural networks work. Why don't we go into Excalidraw and describe how this works? Let's do it together, everyone. Reset the canvas. Okay. So in a normal feed-forward neural network, we're going to have a whole bunch of matrices. Let's do this. So we'll say something like this. This is normal feed-forward neural network. These are layers. And in each layer, there's a whole bunch of numbers. A whole bunch of numbers. Yes, it's for AI. Yep, you're right. We're doing it for AI. Oh, hey, we got a member. Hey, we got This is a feed-forward on the top. This is a convolutional. So we're going to create a picture of an image here. All right, so this is a picture of a cat. Let's just say this is a picture of a cat. Cat, right? The cat has a whole bunch of pixels, right? A bunch of pixels. So let's draw that right here. Cat is made up of a bunch of pixels. All right, trying our best to put pixels on the screen. Here we go. Let's copy here. Let's copy and paste that. Cat is a bunch of pixels. Okay, here we go. Pictures made of a bunch of pixels, you guys, and that's ADHD talking. Oh yeah, also like the implemented by the bachelors was a little too theory. Yeah, a little too much theory. I need application. I need to use it. Cat is very pixelated. It is a very pixelated cat. It's a low resolution cat there. You're catching up. Okay, so this up the top here, I'm gonna sort of divide this really quick so you can see. We're talking about two separate things here. At the top of the screen is your traditional feed-forward neural network. Convolutional neural network is going to involve typically two-dimensional data. What we're going to do is we've got filters here. These are filters. We treat them differently. So what we're going to do is we're going to capture 4 of these pixels at a time, and we're going to move those pixels over let's draw this. Those pixels are going to be run through this matrix here, and you're going to get an output. And it's going to construct the output result of another layer here. You're going to run through these 4 pixels, and it's going to give you an output like this, bop, like that. So 7, and that's going to be the result here. And then you're going to run through, again, you're going to grab these, run that through as well, and that's going to give you some more pixels. And it's going to render out here. Then we'll go 7 again, and that's going to whop right there. And we're going to do that again with this a third time because we have 3 filters, and we're going to create another output here, another set of data, until you get down to just like information about whether you want to detect a picture of a person, right? Or if it's a cat, like how far down the path do you want to go? And then you pass that back up through a traditional feed-forward neural network, right? Right back up here. There you go. So that is what we're looking at here. You can see this, right? So you've got a picture of a glyph, like a picture of a letter A, that will be passed forward in the feed-forward neural network. You'll take just the clipping, right? You step through it, you grab all the pixels, a little bit of pixels at a time, and then you run it through each of the filters, and you create a whole bunch of outputs, which gives you the next input for the next convolutional neural network, the next convolutional layer, which are a whole bunch of filters, right? Usually like 6, so this one has 16 filters, 16 10 by 10 filters, right? Let's count that. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. There we go, 16. And they're 10 by 10. So you create that, pop that out to the next, and then you've run it through a deep feed-forward network, a standard traditional dense layer, fully connected layer, where everything is going to be multiplied by everything. That's the convolutional neural network. If you have any questions, let me know, because that is kind of how that works. Let's jump into the code now. We've got 30 minutes left to get into the code, and we're going to be doing that part next. Okay. Let's delete all of this stuff because that's all the tutorial stuff. We don't need to bother with that. Torch NN. Import torch .nn as NN. Neural network. Import torch.vision. No. .functional. I'm not used to using... This is different, you guys. If you're familiar with Pytorch, we're going to be sort of taking like... It's sort of like the side door. It's not the front door. It's the side door of Pytorch. Sometimes I get a little lost in all the dimensions, especially when you have 3 channels and a bunch and a batch dimension. Oh, the batch dimension as well. Yeah, exactly. It can get complicated. You're right, it sure can. Because the reason why we do batches, it's not because you need to do it from a mathematical perspective. We need to do it because of the hardware constraints. Right now, you do batching because you want to submit the batch over to an accelerator. That process of submitting work to an accelerator has significant latency, right? So all of your work is on a CPU right now. So you say C, right? All the memory's on the CPU, right here in the memory system. When you want to transmit that over to the GPU, right, or the accelerator, the beefy, powerful GPU, right here. That has latency right here. This is slow. Right here. That's slow. So you say like, I don't know, this is like, I don't know, 1 millisecond or something. Something like not very good. Maybe it's like 10 milliseconds. Because if you transmit all that data over to the GPU, once the data's in the GPU, now it's got access to it in its own memory registers, and it can start parallel processing it across all of its cores. Because it's got a whole bunch of parallel processing cores. Did we say as F here? So that's why we do batches. That's what I'm saying. We have batches because this part right here is the slow part. Right here, this is slow. That is very slow. This process of sending the data over to the GPU. Therefore, we do it in a batch, so that way we don't have to introduce latency for every single training sample. We can pipe that over, boom. It can process in a giant batch, and you get that real acceleration power all at once, and you get the output, the result. So you're good to go there. Going to be black and white, so pixels on or off. 6 output channels, 5 by 5 square. 6 output channels. Okay. So this is a 1 in to be the same. So 6 and 6 need to be the same, and you'll have 16 outputs. And the filters will be 5 by 5. Okay. And a fine operation. Okay, then we do the linear feed forward. Okay. So this is exactly what we did, almost to the letter. What we do, oh, look at that, that's neat. This is almost exactly the same. So we had two CNNs, right? What do you call that here? Let me pull this over here, right? Layer 1, layer 2, 2 convs, net, and it's going to be, okay, I'm just gonna call it a self, nothing special. Def init, self, I assume there's nothing else. And then we're going to have our conv1 equals, we're going to save that as self.conv1 equals inn.conv2d with it 1, 6, 5. Okay. We'll do self.conv2. It's the same thing, except for we change it up. We go 6. Are chaos theory and game theory hard? I don't think so. I think those things are easy. I think they're pretty straightforward, right? Okay. So that gives you the error and loss. Is that what you were talking about? Is that what error coding is? That's what I call error coding in this case. There's also test-driven development, which could also be a thing where you start out writing your test first, you run the test and they fail. And your job is to make the test pass. That's also error coding. Okay, let's finish this and then we gotta head out here. All right, so we're gonna create a view to flatten the data. Num flatten features, okay. So x view out equals out.view -1, and it will be self. Wait, number of flat features. Oh, it's a function. Oh, look at that. Okay. We're going to write ourselves a little function there. Num flat features out. There we go. Okay. And then we got some ReLUs and feed forward. Okay, let's do that first. This is like taking the side door. This is taking the side door approach. What language? This is Python. We're doing Pytorch. We're doing Pytorch experts together. Let's do it. We're going through every single Pytorch tutorial, even if it's really basic. We're going through it. We did one entire walkthrough last week. We're doing part 2 this week, and then we'll be doing more next week. And then eventually we'll start building some real models. It's gonna be exciting. All right, we're gonna wrap up here. Here, we're not done yet. We're gonna wrap this up real quick. Okay, I want to do the rest of this here. All right, so we're just gonna do feed forward, a simple feed forward. 1, 2, 3, okay. Out equals F, or is it self? It's gonna be self, right? Oh, we're gonna activate ReLU. We'll go self dot linear 1 with out in it. Here we go, like that. We're just gonna copy and paste that a few times. Increment, increment, and we don't ReLU on this last one. It's gonna be a linear output. All right, so that is 1, 2, 3. And we return out. Finish this last function and we're gonna wrap up here. Here we go. All right, define, we're gonna call this num flat features, the x value, x, let's call it x. Self comma. And what is this gonna do? Okay. So this is going to get us the size. All dimensions except the batch dimension. Okay. Size equals x dot size colon 1. Like that? Yes. All right, we're good to go. And we want num features. Num features equals forward, S. Did we flip the wrong way? Oh, thank you for the error. I see what you did there. Thank you. We would have been confused. We would have been like, something's wrong. 1 colon is the answer. Hey, Forerun, thank you. Thank you for paying attention. Oh, that's great. Yay. Very nice. Almost typed it perfectly. Just got one little thing wrong. Okay. So that is nice for us. Okay. So let's see if we can do something really quick here. Let's do a torch.rand. We'll go a 10 by 10. Can we do that? What resolution does this need to be? We'll do a 10. Does it need to be... We'll find out. We'll find out. All right. R equals. And then we'll say our LeNet. It's going to be a LeNet. Okay. LeNet equals LeNet. Okay. And we're going to say LeNet R. Out. Let's see if we can get this to work. Print out. There we go. Is the second row all columns? 1 column. So this is excluding the batch. So this will take us 1 dimension down. So this excluding batch size, it gets us the exact resolution that we're looking for. We're going to see if we can do one feed forward, and if we can without getting an error, then that counts as winning the day. And then we will continue tomorrow with more. We'll get more going. All right, let's try that. CNN is going to give me an error. The net object is not callable. Wait. This is Python fundamental stuff here. What do you mean it's not callable? I'm just trying to make a new one. It sure is. It's right there. What do you mean? Wait, the new Python is a little bit nicer. Oh, what? Object. Let me do that. No, LeNet object is not callable. Oh yeah, it is. Oh, it's not callable because we didn't make it a model. We didn't. Oh, got it. Okay. Then we just say dot. Let's make this bigger. Can we do that? Nope, not. Given groups, group size of 6155, expected input 1. Oh. In your 11th and 12th, you had computer science as an optional subject. You learned HTML, SQL, Python, and some AI fundamentals while you got yourself worked with some CSS, JSON, and modified and expire. That's really good initial knowledge that you got there. I'm going to try apply deep learning for feature matching. Oh, there you go. The good experience. Oh, good experience. Modified experience. Got it. Okay. Got it. That's really good experience. Good. Very nice. You're on a good track there. Okay. Given groups one. I want to solve this really quick, and then we're going to wrap up here, you guys. Let's see here. Got 10 channels instead. Let's do 1. How about that? Like that better? That better? No? Okay. Calculated, padded, 3 by 3, kernel size 5 by 5. Kernel size can't be greater than the actual. 5 by 5 maybe? All right, let's try that. Nope. 611 calculated by 600. It's too small. How about 2525? Is that good? Nope. Okay. 16 by 9 and 80 by 120 is wrong. Oh, now we're further down. Okay. So we're getting through some other challenges. Like the problem now is right here. Okay. So if we comment that out, that might be better. Let's comment this out real quick. Let's comment this out here. Okay. Let's see if that runs through. Hey, all right. One step at a time. One step at a time, you guys. Hey, all right, there we go. Now this is where it fails, on this part right here. Here we go. Yeah, right there. All right. So we at least got ourselves a potentially partially working convolutional neural network following the side door of Pytorch, not the front door, because the front door I usually think is more like it's going to use some of more of the built-in constructs when we're connecting each of the layers. This is manual. This is like the manual process of connecting each of the layers, which is fine. We can do that. I usually like to do a sequential model, which defines everything for us, all easy peasy. The thing that's making it challenging to do a sequential model is that when you're passing your output from a convolutional neural network into a linear layer, you need to do some extra steps. And right now we've got a bug. All right, where's our bug at? It's somewhere likely in here, right here. Views -1 views, num flat layers, self x. X.size, 1, number of features, 1, for Sn, features times equals S. Okay, so we're gonna have to mess around with this, and we'll have to figure that out